Hi everyone, it's so good to see you all today. I wish that I can be with you all present in Sweden, but I think Singapore just kind of sort of opened up to Europe right now. And with the number of COVID cases going up in Singapore, it becomes a little bit more difficult to actually be there in person. But nevertheless, we hope that through this presentation, we are able to share some of our experiences on how you might be able to benefit as well on how you can use software engineering analytics in supercharging your team. So the way this talk is going to look like is that I first share the approach on how we solve the problem, and then Jeff will talk about the BI stack. And I think later on, Jeff will share his own set of slides so that I don't have to keep pressing forward as he speaks. That would be, I think, easier for Jeff as well. So here's a brief background of how Hubble looks like in 2019. It used to be a very small company, about 5-10 engineers. And at that point, it was very easy for us to actually figure out who's doing well, who's not doing well, who needs help, so on and so forth. That we don't need any form of data-driven decision as much as where we are today. Today, the team has grown 4 times. Now, the whole company is about 50, 60 people, and about 60% of that are actually engineers. With multiple engineering teams running alongside many others, it becomes more difficult for me and our engineering managers, our CTO and CEO, to figure out really, where the bottlenecks are, how can we improve the productivity of the team. So we need some way to actually help our engineers be more productive, as well as help the management team find out where we can allocate more resource so that we can reduce the bottleneck. So here's the advantage that we all have is that there's data. There's data everywhere. In fact, we might not be very cognizant about it, but for most of us, we are using Git. And every activity that we are doing on Git is actually something that we can go back and analyze. For example, every time we do a commit, uh, I can know, who did the commit, when the commit happened, how many lines of code are there, how long did it take for that commit to actually reach production, so on and so forth. So with all those data, we can actually take a step back and say, it's not just good for us to commit our code and make sure that Git or CI/CD everything is working right. We can also actually use those data to see how we can help our engineering team do better. So I might not be able to go through all the examples of the analytics that we have done, but in the next 10 minutes or so, I'll share as much as I can, and then I'll go to Jeff, and Jeff will share the BI stack. And then afterwards, during the Q&A, if you have questions about it or anything that I am not able to cover, I'll be more than happy to explain more as well. So here's some of the problems that I run into as a VP of engineering. How can I help my team be engaged? It turns out that a research was done in 2013 by a company called Gallup. And what they found is that highly engaged companies, highly engaged employees, outperform their peers by as much as 147%. What that means is that as long as my team is highly engaged, I can actually get one free headcount and a half, because that's 147% increase in productivity, and that's for free. So for me as a VP of engineering, it's very important for me to make sure that the engineering team is as productive as possible, because that's how I create value for the company. Another research was done by Microsoft, and this was presented a couple of years ago at Wharton, where they found that the moment you hit 20% overtime a week, the engagement rate of an employee drops by as much as 1.6%. 1.6 times. And so it's important for us to actually see our the activities of our engineers. How many of them are actually committing code within work hours compared to outside work hours? So here's an actual graph in our team that in the past 2 years, we can see that it went up from about 7% to now it's about 15% over time. It's going towards a trend whereby it's not sustainable. Without this information, the way that I can get this information is simply from one-on-ones, from hearsay, from pat on the back and say, something is wrong, but there's no concrete data for me to actually detect this. And this is very well researched in the scientific field. So if I'm able to detect this or have some form of signals from GitHub, GitLab, or whatever code repository we are using, it becomes very easy for us to say, hey, something is wrong. Here's the data. We have to fix it. Now we can prioritize instead of shooting all over the place and trying to figure out what to do next. Here's another question that I always have. How can I protect the company from knowledge decay? Think about it. Now we have the great resignation. We have engineers who are coming, working for 1, 2 years, 3 years, and then they're going to go away. And then we have to hire a fresh set of engineers to actually replace them. And that happens all the time. You do it, I do it, everyone does it. That's just the way the industry works. But so in the tech industry, there's this thing called the bus factor, which is in our lingo, the way it works is that how many engineers does it take uh, for them to get hit by a bus for the project to fail. So we want to actually find out which projects are in danger of engineers leaving the company and no one taking over, and now it hurts the company's productivity. So what we did here is that we tried to analyze the number of commits that were done throughout the history of a project to see which project are in danger and which project are fine. So here you can see, for example, the first project in the green box, we can see that John, Cheryl, and Sandy, they have commit count that are very, very close to each other, which means that the project is fine. It's safe because they have a lot of shared knowledge, such that if even one of them leaves or two of them leaves, I can still sandbag the damage that it will do to the company. But look at number 4, for example, the one in brown, where Dawson has a significant amount of code contribution for that project, but Pradeep and Vishal has very few. So now I can actually go to Dawson and say, hey, Dawson, instead of you continuing to commit your code and writing code there, why don't you actually delegate your task to Pradeep and Vishal, and then you can coach them on how to do their work properly. So then eventually for that project, we can sandbag the damage if Dawson leaves. I can also see now that in project number 5, the one in the red box, that Enrique and Carl, the two people who has a significant amount of contribution for the project, has already left, and Pragati is the only one left in the team. Now I can start thinking, if Pragati leaves, this project will be in danger. In fact, it is in danger now. So now I need to hire more people or transfer one person to this team so that we can sandbag the damage in case Pragati leaves the company. So this is very important for us to actually protect the team and protect the company as well. It's likewise helpful for employee morale. Here's another question that I usually run into. How do we know that our velocity is good? How do we know that the engineers are actually delivering at the best possible speed? So how to do that is you can actually use a value stream analytics. And here's how it works. For most of us who are following the proper process in terms of committing code all the way until deployment, there's a time from first commit to actually you creating a pull request or a merge request if you're using GitLab. And in between that time, I can actually see the average, whether it's going up or down. If it's going up, it means that the engineers are taking so much work and the customers are not enjoying the value because it takes so much time for the commit to hit a PR. I also want to know between a pull request to a merge, how long does it take for the pull request to be reviewed, to be approved, to be merged? The longer it is, the more problematic it is. Likewise, after a code is merged, how long does it take to actually reach the customer's hands? How long does it take for a merge? All the way until deployment. So here we see in the graph, I can straight away see that there's something wrong between the pull request and the merge. It's likely the case whereby, number one, the person who's reviewing the code is getting overwhelmed. Probably he went on leave. Probably he resigned. Probably there are new engineers who are having so much bugs in the code. There could be all sorts of reasons. But without this kind of analytics for me to actually see, I cannot take a step back and go to the engineer and say, something is wrong. We have to fix this. Again, without software engineering analytics, the best recourse we have our one-on-ones, which are very unreliable because you're looking at very specific information, which are always very subjective. Here's another one. How do we reduce defect density? For most of our engineers, we actually want to write quality code. We want to make sure that the code that we write is something that we are proud of. However, we also know that that every software engineer is unique. Uh, our definition of done is unique. The excitement that we enjoy whenever we say that we are done is different as well. So it's good to actually go back to science and see, what the research is telling us about this kind of things. So it turns out that there was a research that was done between Cisco and SmartBear, whereby they found out that the sweet spot for every commit size is about 200 to 250 lines of code. And here's the idea: if you try to review a code before that goes beyond 500, 1000 lines of code, it gets very difficult for you to actually wrap your head around that amount of science. It's just the nature of things whereby you have to limit cognitive load, which is why we want to write readable code as well. So the sweet spot is 200 to 250. Anything beyond that, the capacity for the reviewers to detect defects in the code goes down. So you want to actually have a way to show your engineers, okay, for each of your commit, how many lines of code are you putting in as compared to your peers, and whether it's actually hitting the sweet spot. So here what we are seeing is that for each of the engineers, we can see how they are performing week on week and how they compare against their colleagues. Again, this may not be fully indicative, but it will help us ask questions. So, for example, we can see that it seems that Anthony is doing quite well. Perhaps you can argue that Anand is doing quite well, likewise Jasper. But we can also see that Bella, Dawson, and Janice might have some areas to improve in terms of how we see their historical patterns look like. So without this, again, it's very difficult for us to make this analysis. And now during one-on-ones, it will be more difficult as well for the engineering managers to share with their engineers what's going on and how they can improve. But with real concrete data, we can now take a step back and say, maybe these are the areas that you can improve on, and likewise make it easier for the engineers to improve. There's a lot of things that I still want to share with you. However, I think for the benefit of everyone, it might be good as well for Jeff to share the tech stack that we use in order to solve this problem. Very quickly though, some of you might have actually read about the DORA metrics, especially those doing DevOps, and some of you might have read the book Accelerate and the DevOps Handbook. So let me just quickly skip a few slides. I just wanted to share as well that we are also tracking the 4 key DORA metrics. Very quickly, these 4 metrics: deployment frequency, lead time for changes, time to restore service, and change failure rate. You can read this elsewhere. But then later on, if you have questions or we have more time, I can also go down and discuss more of these. These 4 are important because these are indicative of a high performing team, whether you're a startup or a very successful 1,000 manpower strong multinational company. I didn't discuss this because the resources are abundant. The items that I discussed are the things that is very difficult to find elsewhere, which I hope is very helpful for you. With that, I'm going to pass the microphone to Jeff, and he'll share with you the BI stack.
Thanks, Julius, and hello to everyone. Bear with me for a while I figure out how to actually share my slides. One moment. Maybe Julius, could you help provide me a confirmation if everyone is able to see my slides?
Yeah, we can see the slides.
Okay, so I'll try to wrap up my section of the section of the slides within 5 minutes or less. So what you're seeing now is basically the high-level analytics stack overview of how we actually ingest data from our GitLab repositories all the way up to our data visualization tool. which is which we actually shown to that we'll be using database. So firstly, we start by sourcing what sort of data we want to actually collect for our analysis and subsequent visualization. So there is an API documentation website for the version 4 GitLab API, which we actually explored and picked several URL addresses for us to subsequently call in the data. So with respect to each of the URLs, we tend to store the data in its own dedicated tables. When fetching data, we use a Python request package to basically bring in the data, and the data comes in JSON format. So JSON data format, it's kind of, in a sense, a semi-structured data. It's not really columnar, but it does contain several metadata tags or JSON tags, which gives us an understanding of the context behind a particular value. So how do we actually transform this information from a semi-structured data to a structured data? This is where the Python pandas package is then being used to do the necessary data massaging, data transformation, reordering of the fields, kicking out fields which, or rather eliminating fields that we feel that it's not necessary for our final analytics. And then with the same package, we then converted the data into a CSV file, and then we can subsequently store it in any cloud storage solution, for example, the Google Cloud Storage. So in terms of how we organize our files, we usually place each CSV file in its own dedicated prefix. So for example, we have a dedicated prefix for merge requests, a dedicated prefix for GitLab projects / repositories, so on and so forth. Then with now the files being stored in cloud, we then need to move the data into a data warehouse. So in Google's context, this is where you use Google BigQuery to basically look through via script interface the contents of the files in the CSV and to write it into its own dedicated data warehouse tables. So the commits CSVs goes into its own commits table. Each merge request CSV goes into its own merge request tables. And depending on the nature of, and also the volume of the data and how it grows, we have two modes of how we update this information. If it's considered a master data table, for example, the entire list of GitLab user profiles in our company, we simplify our codes by just doing a full truncate of the tables and refresh and just doing a full load of the data. For highly voluminous, highly transactional data like GitLab commits, we make use of each of the table's own delta flags or delta date flags. For example, the updated timestamp, and we use that as a basis for us to update our existing data warehouse tables to its latest version. And following that, you can use a visualization tool like Metabase as long as it's a connector to the data warehouse that you're using. You can straight away connect to those raw tables. Or if you want to do more advanced or more detailed analytics, we could basically transform the data using Python scripts, or write custom SQL scripts to be run / executed with the front end tools during runtime. So in terms of how we actually orchestrate the entire end-to-end process, we are currently using Apache Airflow. And as you can see, most of that tasks has its own name. For example, load available members. It's basically one task. What we're going to do in one single task is that we call a particular API. We do the necessary conversion to a structured format, create the CSV file, deposit it, and then subsequently move the data from a CSV, read the data from the CSV file into a BigQuery table. So depending on whether a particular call requires information from a subsequent call, we will then arrange those tasks either in parallel to save time or in series. This is basically an overview of some of the data modeling that we actually carried out. If you can see on the top right corner, the two tables, for example, shown here, project mappings team and project mappings labels. Those are actually sourced from the local CSV files that we have. Because currently GitLab doesn't, as far as we know, GitLab doesn't provide labels as to what particular team an engineer or a contributor belongs to, or what sort of what product a particular GitLab repository belongs to. So we do come up with our own lookup tables. It's as simple as just creating a file, running manual codes to actually upload those lookup tables into the final data warehouse tables, and then just refreshing the data visualization tools. You'll be able to see.
Sorry to interrupt. Is it possible to bit zoom in? Because
sorry, I think there was a question.
Bit zoom in, it will be a great help. Because,
I'm not familiar with Meet, so I'm not sure how I could do this actually.
Cool.
Yeah,
it's fine. PowerPoint?
Yeah, this presentation.
Yeah, absolutely. Like we are also recording the session, and also will it be possible for you to share the presentation later? Our participants are asking.
Oh, sure.
Perfect.
Oh, you don't have the copies on your end yet, right? So yeah, we can, right, Julius? Do we have to do any scrubbing of the slides?
I think it's fine. Maybe after this we will share with Brigitte.
Yeah, sure. I will be sharing with the community. Thanks a lot, Jeff. Please proceed. Thanks.
Okay, thank you very much. Yeah. So challenges that we observe, there are a couple of challenges, but I'll just highlight two of them. First of all, we do notice that the commits transactional data for every single record doesn't really come with its own primary key. So we have seen cases whereby, arbitrarily speaking, during the first half of the year, commits were actually tagged to a person named John and with this particular email. And then during the second half of the year, although it is the same person, somehow the display name has been changed to John Wick, although this person has identified, this commit has actually tagged it to the same contributor's email. So in order to actually work around this, we once again had to do a stock take of all possible name and email combinations that are available in the entire commits table. And then we have to actually come up with a mapping table of sorts, basically all the possible names, all the possible emails, and then the third column, which is the primary key, the unique contributor or unique contributor of the GitLab contributor. We manually fill those up as we validate person by person if this comment is done by this particular person, and then we move this information into the data warehouse table, and we do the necessary modeling. Number two, which is basically a common feature, especially when an API call is intended to bring in large volumes of data. By default, there is a pagination that's involved. So with relatively fundamental Python functions, right? For calls like this, you would like to do a while loop, and every time a loop ends, you would like to check in one of the tags in the response body. For example, in this case, x-next-page, whether a value has been generated. So if a value has been generated, it could be a number, it could be a Boolean value, whether it's true or false. We will then decide the next step for the loop, whether you would like to break the loop if it's the last page, or just increase the counter by 1, so that you could start ingesting the information from the following pages as a result of the call. So we reached the last portion, the last set of slides. Since we'll be sharing the slides, I would like to share basically a list of APIs that we're currently using in our software engineering analytics, so that whoever's interested to start developing their own stack, start developing their own pipelines, they now have a head start. Okay, so yeah, that's the final slide. I guess it's time for us to open for Q&A. Thank you.